Picture this. It's 1970. The U.S. Navy is pushing the absolute limits of deep-sea exploration. We're talking advanced submersibles, futuristic tech, super ambitious missions. But something simple, something small, kept bringing their multi-million-dollar operations to a screeching halt.
And the key to this whole crisis, and more importantly, its solution, is right here in this document. Now, I know it doesn't look like much, right? Just some old technical handbook from over 50 years ago. But inside is the story of a massive engineering challenge and a race to conquer one of the most hostile environments on our planet. Okay, let's get into it.
So, what was the culprit? With all this incredible technology, all this hardware designed to withstand the crushing pressures of the abyss, what was the weak link? Well, the answer was surprisingly simple and just frustratingly common: the humble electric cable. To really get why these cables were failing over and over again, we first need to understand the absolutely brutal environment they were being thrown into. This was so much more than just getting wet.
You know, the deep ocean is basically a trifecta of technological torture. First, you've got immense hydrostatic pressure trying to crush everything. Then you have corrosive salt water that just eats away at metal. And on top of that, you have the constant physical stress of dives, flexing, and maneuvering. Cables that were built for commercial jobs, or even for regular submarines, they just weren't cut out for this, not even close.
And the results were, frankly, catastrophic. We're not talking about a single issue here, it was a total cascade of failures. As the document spells out, engineers were seeing everything. Cable sheaths were cracking wide open, water was seeping into the core, conductors were snapping right where they were connected. After pretty much every single dive, the cabling needed a full inspection. It was completely unsustainable.
So, in the face of these repeated, complex failures, the Navy's solution wasn't some new wonder material or a crazy piece of hardware. Nope, the solution was knowledge, all organized and laid out in a single, comprehensive guide.
Now, what's so telling is this one line right from the introduction. The real problem wasn't that people weren't trying hard enough, it was a total lack of standardized information. Different engineering teams were basically starting from scratch every time, using their own proprietary designs or just hoping a commercial cable might work, because there was no central playbook for how to build for the deep ocean.
And this was the answer. This handbook literally became the Bible for deep-sea cable design. It systematically broke down every single component, every material, and every environmental factor. It created a shared foundation of knowledge that would finally make reliable deep-sea operations possible.
So, how'd the handbook actually solve the problem? Well, it broke everything down, starting from the inside out. Let's begin with the conductor, the very nervous system of the entire submersible.
The first big choice was the material. On one hand, you had copper, the reliable workhorse. Everyone knew how it behaved. On the other, aluminum was really tempting. It's much lighter, which is a huge deal for submersibles. But it came with these fatal flaws. It forms an oxide layer almost instantly that acts as an insulator, leading to bad connections. And under pressure, it suffers from something called cold flow, which means it slowly deforms, causing connections to get loose over time.
This chart really drives home the trade-off. Looking at the data straight from the handbook, you can see exactly what the engineers were looking at. Sure, their tensile strength is pretty much the same, but look at that conductivity. Copper is just way better. For reliable power and data in such a critical environment, copper was the clear, much safer choice.
But the material? That was only half the story. The handbook went into incredible detail about how the physical construction was just as critical. As you can see in the diagram, it wasn't just a matter of twisting wires together. Methods like rope lay, where you twist bundles of wires into a larger rope, gave the cable immense flexibility. A single solid wire might snap after just a few bends, but a properly stranded one could handle thousands of flexes, literally the difference between mission success and mission failure.
Okay, so with the course selected, the next challenge was how to protect it. The insulation and the outer jacket were the armor standing between that vital conductor and the crushing, corrosive deep ocean.
The handbook lays out a whole arsenal of materials, and each one has a specific job. You have to think of it like layered armor. You'd start with something like butyl rubber. It's fantastic against moisture, a perfect first line of defense for those inner protective layers.
Then, on top of that, you might add a layer of nylon. Now, nylon's not a great electrical insulator, but that wasn't its job. Its job was to be tough. It was there to provide a rugged outer shell that could resist getting scraped up, abraded, or damaged during servicing.
For communication cables, polyethylene was the go-to.
It had these superb electrical properties that stopped signal loss over long distances, and it was also lightweight. It was the perfect tool for that specific job.
And for the absolute most extreme conditions, you had Teflon. It's incredibly resistant to heat and chemicals, the real high-performance option. But it was crazy expensive, and just like aluminum, it was susceptible to that cold flow problem, which meant you had to design around it. Every material was a different piece of this really intricate puzzle.
So, after all this, what can we really learn from a 50-year-old engineering document? What's the real lesson from this whole deep-sea cable crisis?
Well, I think the biggest lesson is that progress isn't always about the flashy new invention. Sometimes the most important innovation is the painstaking, unglamorous work of just mastering the fundamentals. The Navy's deep-sea program couldn't move forward until they solved their boring cable problem by creating a shared language and a systematic way to design them.
And that leads to a final thought for all of us. From data centers to spacecraft to the AI that's changing our world, everything is built on these incredibly complex systems. And this story is a great reminder to ask ourselves, what is our underwater cable? What seemingly minor, overlooked component is the hidden point of failure in the technology that we all depend on every single day?